Assalamu alaikum dear students. Previously we discussed Ampere's law. Now we are going to discuss Faraday's law of electromagnetic induction. Electromagnetic induction means inducing EMF across any coil when there is change in magnetic flux. Whenever magnetic flux across any coil or any surface changes, it induces an EMF. That EMF is known as induced EMF, and as a result it induces in current. That current is known as induced current, and that magnetic flux is given by B dot dA. This is similarly defined as we defined electric flux. So Michael Faraday performed several experiments in 1831, and he concluded his result with 3 experiments, and we will discuss these 3 experiments. For example, in first experiment we have magnetic field that B is into the page, and he placed a coil in that magnetic field, and this coil has certain resistance R. So he moved this coil related to this magnetic field to the right direction. For example, it has velocity, certain velocity, and we move this coil to the right direction. As a result, an EMF is induced in this coil because it has relative motion with respect to this magnetic field. So that EMF direction is given by Lenz's law that we will discuss later. So current and EMF direction are same. That EMF and the currents are known as induced currents and induced EMFs. And in second experiment we have same magnetic field into the page, B into the page, and we place same coil. It has finite resistance, and now this field is produced by a magnet, and that magnet has certain velocity to the left. So we move now this magnet to the left, but coil is stationary, so velocity of coil is 0. Only the magnet is moving related to this coil. As a result, an EMF is similar EMF, same magnitude of EMF is induced in this coil. So there is also relative motion between the coil and a magnet. And in third experiment, he carried a electromagnet and placed coil in the field of electromagnet. And the electromagnet is a magnet in which you can produce magnetic field by passing currents. So whenever you pass current through this electromagnet, you can produce a changing magnetic field. When you will change the amount of current across this electromagnet, you can change the magnitude of magnetic field. So when you place this coil into the magnetic field of this electromagnet, again EMF is induced in this coil. So here both have velocity 0. So Faraday concluded that here in this case, in first case, it's magnetic force that is causing flow of charges, because whenever a charge moves across a magnetic field, it experiences force. But in these two cases, 2 and 3, it's not magnetic force that is causing the flow, because both coils are stationary. Only magnetic fields are changing. So he concluded that only the changing magnetic field, only changing B fields or magnetic fields induce EMF. Because induced they induce electric fields, changing magnetic fields, B fields, induce E fields, electric fields, and these fields are known as induced electric fields. Induced E fields, and these fields are non-conservative fields. As we previously discussed, electrostatic fields, that in Coulomb's law, those fields were conservative fields, but these induced fields can also exert same force, and that force can be given by F is equal to Q into E. So these induced force can also exert same force. So that EMF in three cases that we discussed in above, 1, 2 and 3, magnitude of EMF is same. And that is given by, that induced EMF is given by minus d phi by dt, and here minus sign is due to Lenz's law. So only changing magnetic flux can induce the EMF. So whenever there is change in magnetic flux across any coil, it will induce EMF. So for example, we have a surface and there is magnetic field in this direction. So this is surface. So direction of area is this, and there is angle between them. This is B. For example, if phi B is not changing, magnetic flux is not changing, means constant, then EMF induced will be equal to 0. But if we increase B with time, for example, its first magnitude was this, now we have increased the magnitude of B. Now means this quantity d phi by dt is greater than 0, means we are increasing. As a result, EMF will be less than 0. So EMF will be in such a direction that it will oppose this magnetic field that we are changing across this coil. So new magnetic field that is produced by this EMF that is induced in this coil will oppose this magnetic field. So that magnetic field will be opposite to this magnetic field. So EMF will be in this direction, because if you curl fingers in direction of this EMF, so magnetic field will be opposite to this magnetic field, external magnetic field. So if you have this positive quantity, then EMF will decrease. And if for example this quantity d phi by dt is less than 0, then EMF will be greater than 0. So whenever this is negative, because here it is also negative sign, so negative will cancel, and as a result EMF will be positive. So EMF always is in such a direction so that it produces a magnetic flux. That magnetic flux will be always opposite to the external magnetic field. So that EMF we can write also EMF here by this formula, that is E dot dl. In electrostatic case we had E dot dl equal to 0, but here in this case it is not 0. So that EMF we can write, because we know that EMF is equal to d phi by dt. So we can write here E dot dl equal to minus d phi by, here it is, magnetic flux dt. Or we can write it also as dl is equal to minus d by dt as b dot d, because magnetic flux is given by b dot d. So changing magnetic fields create circulating electric fields. So that is mathematical form of Faraday's law. So now we will discuss Lenz's law. So Lenz's law says that, for example, we have a coil and we have a bar magnet. It has north pole and a south pole, and it produces magnetic field. So when we will move this magnet to the down direction across, and we will change magnetic flux across the area of this coil, so this changing magnetic field will induce EMF in this coil. So EMF in this coil will be in such a direction that it will oppose the change in external flux. So direction of current will be such that current will produce an magnetic flux, and that magnetic flux will oppose this magnetic flux. So magnetic current will be in this direction, so that it will produce a magnetic field that will oppose this magnetic field. So always direction of current will be given like that. If you move this magnet upward, then the magnetic field will support this magnetic field. So EMF will be in this direction, so that it will induce an magnetic field that is produced by this current. Induced current will be in this direction, and that will support the magnetic field of this. So it always opposes the change of flux. So when flux increases in this coil, it tries to reduce that external flux, and if flux decrease across this coil, then it tries to increase the flux, so that the EMF direction changes by changing this magnetic field, external magnetic field.